So let's start with another class for the market risk book. And today we are talking about the non-parametric approach. Okay, so some things that we'll see with the slides and something will go to the book as well. Fairly easy topic, I would say, not a very difficult or something that can take a lot of time. If we understand the basics, I think we are good to go with this particular chapter. So if I have to talk a little bit about the basics here. So far what we saw in the first chapter was that of a parametric methods like a delta normal var. So when I talk about parametric, essentially I mean to say we are talking about something which has parameters. So for example, in a delta normal var, you have a parameter like the mu and the variance. You need this data to calculate the var under the parametric methods. So that is one thing. You need this particular data. And apart from that, it also assumes specific distributions that the data should have. Ideally, normal is more preferred. And then if not normal, then you can also have a log normal distribution. So that is something that we were assuming in the first chapter of this book. But now in this particular chapter, we are actually talking about the non-parametric estimation. Now, as the word suggests, it is non-parametric. That means no parameters are required here. All you need is just the data, no matter what the distribution of the data looks like. It does not make any difference. All we are doing is just we are using the non-parametric and the data that we have. We are using that and we are finding the var or the expected shortfall under this method. Now, within this non-parametric, we have something known as bootstrapping. Now, we don't have to get confused with a bootstrapping of the yield curve when I talk about fixed income. That's a different thing. That's like interpolation. But this bootstrapping is absolutely different concept here. When I talk about bootstrapping, you can think about this bootstrapping from the level 1. There was a chapter, the simulation and about the Monte Carlo, right? In that, we had a bootstrapping method wherein we have a huge data with us, the entire population, and we take out some samples and then we pull those samples back to the data. So that's what we are talking about here. So bootstrapping and the non-parametric, they are data-driven approaches. They do not rely on any specific assumptions about the underlying distribution that we have. However our data looks, it's okay. It's absolutely okay. We can still find var. And these methods are particularly useful for var estimation when rare events occur in the tail of the distribution. Obviously, we are focused more on the rare events, or rather, we are more heavily focused on the tails. That's what this entire market risk is all about. Okay, let's look at the first learning objective, apply the bootstrap historical simulation approach. So it's a combination of a historical simulation method, something that we talked about in the last reading and also in level 1, and then a combination of the bootstrapping method. So when I talk about bootstrap historical simulation method, it's a very simple or rather straightforward method for estimating the value at risk. So how do you estimate the var under this method? Over here, we apply the concept of bootstrapping. Okay, so it involves repeatedly sampling. So you take samples from your original data set. For each of the samples, you will calculate the var. Okay, for each of the samples, you have, let's say, 1000 data points. You take a sample for about 100 data points. And then for that 100, we calculate using the historical simulation method, right? Like separating the quantiles. That's what we do. For each sample, we calculate that, and then we pull or return that data back to the original population data that we have. And this is known as sampling with replacement. Okay, so there is a chance that out of those 100 or 1000 data points, multiple selection in each of the samples is quite possible. I'll show you that pictorially as well. Just 1 minute here. Let me just turn this off. Okay. So pictorially, I'll tell you how does it look. That means the same data points can be repeated or selected multiple times, and probably that can affect the value at risk as well. So the best VAR estimate from the full data set is the average of all the sample VAR that you've taken. How about the expected shortfall when you have a method like a Bootstrap and the historical simulation? How do you calculate that? Well, it's the same process. You take the data, you take multiple samples, and then after taking multiple samples, for each sample, you calculate the expected shortfall, just like we do in the historical simulation method. And then we average it out to all these things. So if we read this out, it's the same process that can be applied to estimate the expected shortfall, where the tail region is divided into slices, like the tail region. If you have a tail like this, you divide that into slice, and average of all above the VAR, you just go ahead and you take the average of that. So this is for the first sample. And then again, you do it for the second sample, third sample. And the best estimate is the average of all the expected shortfalls that you would have calculated. Now, just look at this particular diagram here. You can pretty much understand that this entire thing is our data. Now, the point to note is that this is not a normal distribution. Okay, it's pretty much like a bimodal kind of a distribution. But do we care about the shape of the distribution under the historical simulation, or rather the non-parametric? No, we don't care about that. That's not the assumption that we worry about. So what I can do is I can pretty much take this entire data that I have. I can take out the samples, okay, small amount of samples, and then I can calculate the VAR of each of these sample data that I have. And then all the VAR that I got here, let's say for the first sample, it's $10 million. The second is 5, 7, and 8. I can go ahead and I can just take a simple arithmetic average, divide by 4, because I've taken 4 samples. And the amount that I get, $7.5 million, that is my bootstrapping value at risk. Okay, so Bootstrap historical method is nothing, but you take up these samples, and the same thought process can be applied to ES as well. For each of these VAR, you can just slice the tail here, and you can calculate the average of whichever is above the VAR. So for example, if this is the $10 million, all the quantiles, all the lines that you see above this point, just average it out. Whatever the number that you get, that's going to be your ES. Similarly, the ES for here, here, and here, and then take the average of all the 4 ES. So pretty much a simple method, I would say that, not a complicated method. The point that needs to be noted is that the empirical analysis, what has been seen in the past, is that bootstrapping provides more better or a precise estimate of a coherent risk measure. Now, coherent is something that has 4 different properties, right? And something that's a better coherent is always preferred as compared to a plain historical simulation method. So if you're just calculating the VAR using historical simulation method and the VAR that has been calculated using bootstrapping historical simulation, this is a better and more coherent, because a lot of things are at play and you're taking multiple samples and you're taking the average of that. So you're not essentially dependent upon just one value at risk number. That's the reason this is a better approach. Okay, moving on to the next learning objective, and that is describe the historical simulation using the non-parametric density estimation. Okay, so again, we are talking about historical simulation as well, but in a non-parametric density estimation. Okay, so essentially, if you look at a normal distribution, ideally, normal distribution is also sometimes referred to as a density curve. When I talk about density in mathematics, density means like having a dense area, or like, a curve shape, and that too in a continuous format. So how can you use the historical simulation value at risk? How can you calculate that? Using the non-parametric, of course, we're talking about non-parametric, but then having a density approach, having that continuous distribution or a density curve like this approach. How do you do that? Let's check it out. So the clear advantage of historical simulation is its simplicity. You do not need any assumption. Just arrange the data, pick up the percentile that you want, and you have your value at risk. But the obvious drawback to this approach is that the discreteness of the data does not allow for estimation of VAR between the data points. For example, if you have a data like 100 data points, you may have 1, 2, 3, 4, 5, up to 100. You can pretty much find the 95 percentile or maybe the 96th percentile. You can find that, right? So basically you can find discreteness of your data because every data is discrete, right? But rather, what if you want to find 95.5 percentile VAR? Now this is pretty much, it goes into continuous form, okay? You want to find 95.5% VAR or maybe 95.6% VAR. So something in decimals we are talking about. How could you do that? Well, for that, you need to follow this non-parametric density estimation. You need to find the density curve for that. Okay. And what's the benefit of this? Well, it does not rely on restrictive assumptions because still we are talking about non-parameters and they do not rely on the underlying distribution. Secondly, it allows for VAR calculation at various confidence level, just what we've been talking about, the density estimation. How do you do that? Well, for that, we need to look at the VAR calculation for 95.5. Okay, just a simple example. What you can do is you can connect the midpoints in your histogram bars that you have, which is a discrete data. You can convert that data set into something known as surrogate density function. Now, what do you mean by surrogate? Surrogate is something that is not true. Okay, we have a true population data, which is in the format of a histogram, right? But what we can do is we can convert this true data into something which is a surrogate, okay, which is kind of came from this, but not exactly this, or rather it's a surrogate. It's not true data. That's what we can just say that. So we can connect the midpoints of these things, and then we can pretty much form a curve. So then there must be some data right here as well. Okay. And you just start from here and then you just connect the data in a linear shape and you connect the midpoints. And then what you have is you've converted this discrete data into a surrogate density function, into a continuous function. And then you could probably calculate the VAR at any confidence level, just like a normal distribution. You have a Z table, just like that. We can go ahead and we can do that. Now you can have a look at the diagram here and we can just, so this is the original histogram that we have so far. And what we can do is we can start with the midpoints, mid of the data, and we can just connect these midpoints. Now you must be wondering, okay, that this data is lost. This data is lost. Well, it's not lost. It's covered right here. And if you feel that this data is lost, no, it's not. It's going to be covered here as well. So basically, everything will be covered somewhere or the other, which we feel that it's lost. So ideally, no data is lost with this method. The only thing happening is that the data is being displaced, okay, from one place to another place. So this may come up here, okay, and this may come up here, so on and so forth. That's all that's going to happen. But ideally, you can eventually have a full data that's going to look more and more like a normal distribution, or maybe a density curve, not exactly normal, even if it's a T distribution, fat tails, whatever that is. But it's going to have a density curve. And once you have a density curve, you can pretty much find any area that you want, or you can find the var, or maybe any quantile that you can find. You can go ahead and you can do that. So that's one of the benefits of having the historical simulation method. Yes, you can modify that using the density estimation as well, specifically a surrogate density function, like creating like such and artificially. Okay, that's what the surrogate density function is. So if you have any questions, anytime that you feel like you have any questions, you feel free to ask. Okay.
Okay, sure.
Yeah. All right. So moving on to the next learning objective that we have, and that is compare and contrast the age weighted, volatility weighted, correlation weightage, and then the filter historical simulation approach. So basically the variations that we can have on the historical simulation. Why do we need this? Okay, let's understand. Basically, in reading 1 or chapter 1, we talked about the historical simulation method. And essentially what historical simulation method does is that it gives equal weightage to both the current data and the past data that we may have for all the n observations up to a specified cutoff point, and then that is used when computing the current period var. So essentially, when you create a historical simulation, you just arrange the data, and then for all the data points, you're giving equal weightage. Like for example, if this is the 500th data point, and this is perhaps the 10th data point. So you can imagine if I have 252 trading days in a year, then this is approximately 2 years of data, right? 500 data points. So approximately 2 years of data. So under the historical simulation, if you have n is equal to 500, like we have got 500 data points. So older observations beyond the cutoff are assumed to have 0 weight, and relevant n observations have equal weight, that is 1 divided by n. So I'll explain that. So remember, let's suppose that this is the data point for TCS. Now TCS have been in the market for years now, right? So we just pull up the 2 years of data for TCS. But does this mean that only having 500 data points, that is n is equal to 5, can you disregard the data which was older or prior to 2 years? Like maybe the company started, let's say 20 years ago or 30 years ago, but we are just giving importance to 2 years of data. And that too, if the n is 500, we have pulled up 500 data points. We are dividing those 500 by this 1 divided by n. So that means each data point from 0 to 500, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up to 500, each of them is given equal weight of 1 divided by n. Every weight is similar. No disparity is done whether this is a recent data, like 500, that means yesterday's data, and something that happened 2 years ago, an older data. So there is equal weightage is given to this as well as to this data. Now, why it's a problematic? Because you know what? Maybe let's say that this might have been a crisis data of 2007, or rather 2009. So maybe in the mid 2009, we had the data which was very much volatile. But right now, fast forward to 2011, maybe perhaps the market has been stabilized and we do not see much of any volatility here. But still, a not volatile period, we are giving the same importance, and a higher volatile period, we are giving the same importance as well. So weightage is given. That's a problematic situation. And something that is highly volatile may not exist here. That's another problem. So if the period was a higher volatile earlier, okay, higher volatility means higher standard deviation, right? And if the standard deviation is high, remember in the VAR calculations, we used the standard deviation as well, right? So if this is high, obviously your VAR will also be higher if the volatility is high. And supposingly you calculated higher VAR here, but now when the period is not volatile, when the standard deviation is low, but you still incorporated a higher volatility, a higher VAR. So that is something that's a mismatch. And we'll talk about this in the second or third method that we have. But just get the understanding as to what we are doing here. That's the main priority here. Now, there is something known as a ghost effect. What do you mean by ghost effect? Ghost effect means that a very crisis data has having that shadow effect or a ghost effect, something that really do not exist. Okay, so ghost effect of past event can persist in the computation of current VAR. So when you calculate the VAR using these 500 data points, you've captured the crisis data as well, which is not relevant. So that is the reason we need to change this kind of a methodology where we are confused between past data, which is not relevant, a higher volatility maybe earlier. Right now, we do not have any volatility. Some sort of a thing that we need to do is, and that's what we're going to be talking about, the 4 improvements to the traditional historical simulation method. And that's what this learning objective talks about. Okay, so the first one that we have is known as age-weighted historical simulation. Now, one adjustments that to the equal weighted assumption that we just saw used in the historical simulation is to weight recent observations more and a distant, far off observations less. That is something probably that what we can do. So assume W1 is the probability weight or a percentage weight that is given for the observation that is just 1 day old, that is yesterday. Then W2 can be defined as the W1 weight. So if the W1 is, let's say 99% weight is given to yesterday's data, and then 99% for W1, which is the value here. So W2 will be defined as 99%. And then we are just taking, we're not taking exactly 99. We are adding or multiplying this lambda. Okay, now the lambda may be anything. Maybe let's say 0. It's a value between 0 to 1. Okay, so maybe let's say it's 0.5. Okay, 0.5. So the weight of 2 is now half of this 99.99%. So somewhere around, let's say it is closer to, let's say 49%. So the second weight, so W1, the yesterday data, what's the weight? 99. And day before yesterday, what's the weightage you've given? That means approximately 45. So that means whatever the value that you have for W1, let's say yesterday the TCS stock was around, let's say $150. So you'll be taking 99% of that value. And then day before yesterday, it was around 148. So you'll be taking 45% of that. So that means you are decreasing the weight for all the older observations, because if you look at weight 3, what is the calculation? It's going to be weight 1. Okay, weight 1. That is 99%. And then the lambda square. That's what you do it. So 0.5 square. Somewhere or the other, at this point, at a very last point, you'll reach and you'll realize that is actually gone. Okay, so probably the best way to understand is via this timeline. So imagine I've pulled up this 252 days of data, the past data. So what I'm going to do is I'm going to give weight any weight 1 to this particular thing. And then the 250th data point will have a lesser weight depending on the parameter, which is lambda. If the lambda is 1, what happens? Then weight 2 is nothing but lambda times weight 1, right? So weight is 99, lambda is 1. Again, weight 2 will be 99%. Same thing, if the lambda, so it all depends on the lambda, that how fast you remove the effects of the older data that you may have. Okay, so it depends primarily on the lambda. But generally speaking, this is how you can imagine that what's the improvement here. That means the closer that if we are standing here today, the closer observations are given more weight, and the far off or distant observations are given lesser weight based on this weighting methodology. That's what essentially we are doing here. And if you want to calculate the weight of I for any, I can be any number, okay, the first data point, second data point, any data point that you want to calculate, that is going to be calculated by lambda, whatever the lambda is, I minus 1. Okay, so I, whatever, if you're calculating the weight for, let's say, 15th data point, so that's going to be 15 minus 1 multiplied by 1 minus lambda divided by 1 minus lambda to the power n. That is how many days of data here. N is 252, the data points that you have. Now, possibly this is something that you have to remember for the exam. Do remember that it could be a potential question that they'll not ask you to calculate the data point, but yes, it's a good to know that what exactly is this formula. So just make sure that you remember that.
Yeah, just one question. Like the sum of weights, it would be equal to 100%, right?
Yes, the sum of weights, obviously it's going to be the max that you can give is just the 100%, but it depends. Yeah.
Okay.
Yeah. So it's the sum of weights has to be, you cannot give more weightage, because the entire idea is that now it's not necessarily that the sum of these weights ideally could be 100%, but it totally depends on the lambda, because if the lambda is 1, then ideally you are adding 99%, 99%, 99%. So maybe the sum of weights is not exactly, if you just add this up, it's not coming out to be 100%. Not necessarily. Okay, so that assumption can be just taken away.
Okay.
But the entire idea is that the overall idea is that give more, because we are standing here. Because see, if it was raining yesterday, there is a high chance that it may rain today as well on December 2022. But if it was raining last year, we don't know whether it's going to rain today or not. So why give more, attention or more focus on the something that has happened in the past? That's the idea. So all you have to remember for this age-weighted historical is this particular formula, and just remember the implication. A theoretical question can be made up. That is, the lambda term, which is known as a decay parameter, is between 0 and 1. Okay, so if it is 1, what happens? If it is 0, what happens? Okay, and reflects the exponential rate of decay in the weight or value given to an observation as it ages. So if the lambda is close to 1, as I said, if it's close to 1, that indicates a slow rate of decay. So we're not talking exactly 1. We are saying close to 1, maybe 0.9, 0.95, something like that. A lambda that is far away from 1, or ideally you can say that it's away from 1 means closer to 0, because it can only be 0 and 1. So if it is far off from this 1, that means somewhere here, or maybe 0 or something like that, that indicates a high rate of decay. That means faster and faster, you're giving more importance to this, and you're actually removing these things. So only the most very recent data is used, because there's going to come a time where the lambda, and if you just do that, the weight of 5, 6, whatever that is, ideally they're going to turn out to be 0. So you can remove those observations. And if a lambda is 1, that means there is no decay that is happening. So all your historic data is actually being used. That's what this thing is. So if the lambda is 1, that means you'll not be able to give 0 to any of these values, and all the data will be part of your historical simulation method. So that's what age weighted historical simulation does. As the data will age out, the older data, remove them. That's the idea. And more, if you want to remove faster, then you have to make, it's going to be a close to 1. Sorry, 0, close to 0 is something that you can just think that it's going to be a high rate of decay. If it is closer to 0, the lambda, it's going to be faster, and you're going to be using most very recent data set. Okay, so this slide will be very much useful once you revise this thing. Okay, moving on to the second improvement, and that is a volatility weighted historical simulation. Now, the volatility weighted historical simulation approach, it weights individual observations based on their volatility instead of their proximity to the current date. So it basically captures the effect of the volatility. So the idea behind this is that if recent volatility has gone up, then using the historical, which is a past data, will underestimate the current risk level. Let's say you calculated the VAR up until today, and then maybe later down the line, there's a news that, okay, something has happened. There is any kind of event that is happening here, and that suddenly has spiked the volatility up. But your estimation of VAR, maybe it's, let's say, $10 million, and the current volatility is very much higher. Because if the volatility is high, obviously your losses can go beyond $10 million, right? Because of the higher volatility. So obviously you are underestimating the current risk level if you did not capture the recent volatility, and especially if it has increased. So if volatility has gone up and you've calculated the VAR using older data points like a historical data, then pretty much you are underestimating your risk levels. Similarly, we can say on the opposite side, if the current volatility is it's markedly reduced, and if you have the older data with high periods of volatility, you have overstated the current risk level. You've overstated the VAR, and you've kept this much money as a buffer, as an economic capital in your balance sheet. So no need for that. You need to account for the current volatility. So somewhere or the other, this thing is coming to the picture, and that is the concept of current volatility. That what's the volatility right now? We need to capture that in our data. And this is how you can go ahead and you can capture the effect of volatility. So basically, what we are doing is we are taking the returns, okay, for one single day. We are taking the return, and then we are taking the current volatility time t divided by what was the small t, means the older volatility. So if you can look here, I think this is a much better representative. That means you're looking or appreciating this fact of current volatility estimate, whatever they estimate for current period, divided by what was the estimate of volatility at that point in time, multiplied by the return of that particular day. So if this is a 30 days ago, then the return what was there 30 days ago, and you have your current volatility in the numerator. That's how you can calculate the updated returns. And then you can use this updated returns in your VAR calculations. So rather than just plainly using your return data, adjust your returns with the current volatility estimate, and then use that data to calculate the value at risk or the expected shortfall. So I can use the value at risk using my historical data points, but rather than that, I can go ahead and I can use the updated returns data that has taken into account the volatility estimate, so that I do not overestimate or underestimate my value at risk. That's the entire point here. Thus, the volatility adjusted return is replaced with a larger expression if current volatility exceeds historical volatility on day I. So if the current volatility is higher, obviously the returns will be higher, because if the numerator goes up, the overall answer, it's going to be higher. And if the returns are higher, then your VAR, it's going to be dependent upon that. So you're taking all higher returns rather. Now, VAR and ES and any other coherent measure can be calculated in the usual way after substituting historical returns with volatility adjusted returns. So all you're doing is, the entire core of this method is that you are substituting the historical returns, the plain historical returns, with volatility adjusted returns. So you just need to remember that what's the formula here as well, the current at the numerator and this particular thing. So with the volatility adjusted return is replaced with a larger expression if the current volatility goes up. So the returns will be higher. That's what we are saying here. What are the advantages of the volatility weighted method? Is there any specific advantage? Yes. It explicitly incorporates volatility. I mean, just look at it, considers the current volatility estimate. That's a better approach, a more better and higher sophisticated approach than blindly using the old data. So this method takes into account the volatility of the market, which provides a more accurate estimation compared to other historical methods that do not explicitly consider volatility. So obviously it's an improvement, and that's what we are studying. It is sensible in the near term estimate. So it gives you a sensible estimate. This method produces VAR that are more sensible and relevant in the current volatility scenarios. Okay, so that's a better risk assessment. It's a better risk assessment that we can use this particular thing. And finally, it has a higher VAR estimate, because if the current volatility is high, the returns will be higher. And if the returns are all higher, then obviously you get a better or a higher VAR and a more safer value at risk. So the volatility adjusted returns enable VAR estimates that are higher than those obtained from using the historical data set alone, offering a more conservative or a better risk management. That is what we can, make out using the third advantage of the volatility weighted historical simulation.